Good morning, all of you. Welcome to Sri Jendra and John. In the previous lectures, we have completed S block elements. Now, in this lecture, we are going to start new topic, that is P block elements. So, S block elements we have discussed in the previous lecture. Now, we are going to start P block elements, which is very important. So, in P block elements, we have the now following groups. Let us start now. So, P block elements now we are going to discuss. So, introduction. P block elements, what are P block elements? The elements in which the differentiating electron, that is the valence electron, enters into the outermost p subshell. As 6 electrons can be filled in p subshell. In p subshell, what are the suborbitals? We have px, py, and pz. So in each suborbital, we can have two electrons each. So total p orbitals can withstand 6 electrons. So as 6 electrons can be filled up in p subshell to minimum extent. Thus, there are 6 groups of p block elements. That is from 13, 14, 15, 16, 17, and 18. That is from 13 group, 14 group, 15 group, 16 group, 17 group, and 18 group. These groups starts with the elements. 13 group we have boron, 14 group we have carbon, 15 group we have nitrogen, 16 group we have oxygen, 17 group we have fluorine, and 18 group we have helium, respectively from group 13 to 18. Only to this block we find metals. P block elements only we will find metals, non-metals, and also metalloids existing. No other block, that is D block, F block, and S block, we do not have all these varieties of elements. Only in P block we have metals, metalloids, and non-metals. Next continuation. So what are the P block elements we have? Boron family. First we have boron family, that is NH2NP1, boron, aluminium, gallium, indium, and thallium. Gallium is a liquid metal, and boron is non-metal. Next, carbon family, we have carbon, silicon, germanium, tin, and lead. Germanium is semiconductor. Germanium is what? Semiconductor. It is nothing but metalloid. We'll say it is metalloid. Better we'll write metalloids. And 15th group we have nitrogen family of nitrogens, that is nitrogen, phosphorus, arsenic, antimony, and bismuth. Bismuth is a metal. Arsenic, antimony are metalloids. Arsenic and antimony are metalloids, whereas nitrogen and phosphorus are non-metals. So 16th group we have oxygen, sulfur, selenium, tellurium, and polonium. Polonium is a radioactive metal. Polonium is a radioactive metal. So as I told you, we have 13, 14, 15, 16, 17, 18. And in this 11th class, we'll study only 11th class, we'll study only 13th group and 14th group, 13th and 14th group only. And in 12th class, we'll study about 15, 16, 17, 18. So next we'll see 17th group elements. 17th group elements, as we already know, they are called as halogens or fluorine family. They contain fluorine, chlorine, bromine, iodine, and astatine, and all are non-metallic in nature. 18th group, we have inert gas or noble gases. They have stable electronic configuration. They have either NS2 configuration or NP6 configuration. So exception is only for NS2 configuration. Remaining all they have NS2 NP6 configuration. NS2 NP6. This is the only exception. And argon, krypton, xenon, radon, everyone will have NS2 NP6 configuration. So in any group, first element differs from the remaining members. In always all the groups, any group, you take first group, second group, 13, 14, 15, even you take alkali metals, alkali earth metals, D block elements. In any group, first element differs from the remaining members of their groups due to small size and absence of d orbital. Due to small size and absence of d orbitals. So this is very important. So for example, in the X block elements, you have seen lithium is anomalous to other elements because of its small size and absence of d orbitals. In second group, we have beryllium is anomalous to all. Similarly, in the 13th group, we have boron is anomalous. 14th group, we have carbon is anomalous. 15th group, we have nitrogen is anomalous. 16th group we have oxygen is anomalous. 17th group we have fluorine is anomalous, and 18th group is helium is anomalous. So in all the groups, first elements are anomalous to other members, remaining family members of the groups due to their small size and absence of d orbitals. So please make a note in your classwork. These PPTs should be written in the classwork, then only can understand easily. Next, coming to electronic configuration of p block elements. The general outermost electronic configuration of p block elements is in general is ns2 np126. ns2 is common for all groups, np126. For group 13 it is np1 only. For group 14 it is np2. For group 15 it is np3. For group 16 it is np4. If you see here, boron atomic number is what? 5. So boron atomic number is 5 is 1s2, 2s2, 2p1. That is ns2 np1. Second, carbon atomic number 6, 1s2, 2s2, 2p2. Next we have nitrogen atomic number 7, 1s2, 2s2, 2p3. Like that it goes on. So oxygen atomic number 8, it is 1s2, 2s2, 2p4. So ns2 np4. So you can see similarly for 17th group we have ns2 np5, and 18th group we have ns2 np6 except for helium. 17th group ns2 np5, 18th group we have ns2 np6, exception here it is for helium. In this group helium is only ns2, does not have any p electron. This is the only exception. After first element in every group, there is availability of vacant d orbital, increasing the coordination number. So that's why the covalence increases. For example, boron forms Bf4 minus. The covalence is only 4. Covalency of boron is only maximum 4. Whereas covalency of aluminum is maximum, it is 6. Because aluminum can give AlF6 minus 3 ion. So tetraboron ion and hexaluminum ion. So after first element in every group, there is availability of vacant d orbital, so increasing the coordination number. Next continuation. Atomic and ionic radius. The atomic area of p block elements decreases on moving from left to right in a given period, and increases from top to bottom in any group. So the atomic radii and ionic radii of p block elements decreases on moving from left to right. Anyway, across a period, always atomic radii decreases, and down the group, atomic radius and ionic radii increases due to the increase of atomic number. Due to the increase of atomic number, in any group you take, down the group, that is from top to bottom in any group, atomic radii and ionic radii increases by why they are increasing, because of increase in atomic number and addition of extra shell. Next, ionization energy. The ionization energy of p block elements increases from left to right in a period, across a period, and decreases on descending a group because of the increase in atomic number. However, group 13 elements suffer a decrease in ionization energy than group 2 elements, which is due to fully filled configuration of group 2 elements. So, group 13 elements, if you see the ionization enthalpies, is less when compared to group 2 elements, that is alkyl earth metals, because in group 2 the outermost configuration is ns2. ns2 means completely filled. Completely filled means more ionization energy is required to remove that electron. So completely filled, that's why we can say straightly group 13 elements have less electron ionization enthalpy than group 12 group 2. Group 13 elements have decrease in ionization energy than group 2 elements, that is alkaline earth metals, because of completely filled group 2 elements. Next continuation. Electron affinity. It increases from left to right along the period among the p block elements. So along p block elements, always electron affinity increases from left to right along the period, and down the group decreases. Its value decreases from top to bottom in a particular group. Few exceptions to these trends are also observed. That exceptions we are going to discuss in that particular group. Group 15 elements have exceptionally low values of electron affinities due to half-filled orbitals existence in their valence shell. Group 15 elements have exceptionally low values of electron affinities. Why? Because they have half-filled ns2 np3. The outermost configuration of group 15 is ns2 np3. P is half-filled. So due to half-filled orbitals existence in their valence shell. Similarly, group 18 elements have zero electron affinities due to their stable octet configuration, that is ns2 np6. All other elements will try to attain the stability of group 18 elements, because group 18 elements are almost stable. That's why they will not form any chemical compounds. So these are the general trends of P block elements. Next, we have metallic character. In P block elements, metallic character, as I told you, in P block elements, we have metals, non-metals, as well as metalloids. In metallic character of P block elements decreases along a period. If you see from left to right, they decrease along a period, and any group in metallic character increases down the group. So we observe that elements with strong metallic character are located in the lower left portion of the P block elements, whereas those with strong non-metallic character are found in the upper right portion of the block. Upper right portion of the block. For example, you can see here 13 group starts with what? Boron, non-metal. Ends with, so 13 group you see, 13 group boron, aluminum, gallium, indium, and thallium. So thallium is a metal. Similarly, 14 group carbon, carbon, silicon, germanium, lead, tin, and lead. So ends with lead metal. So next 15 group. So every group, if you see, starts with 15 groups starts with nitrogen, and nitrogen, phosphorus, arsenic, antimony, and bismuth. Bismuth is a metal. So underlined ones are metals. Similarly, 16 group. 16 group oxygen. So 16 group ends with metal. 17 group also like that. So everywhere we observe that elements with strong metallic character are located in the left to lower left portion of the P block elements, whereas those with strong non-metallic character are found in the upper right portion. So these are upper right: nitrogen, oxygen, fluorine, neon, and so on. Next continuation. So you can see here carbon, non-metal, and bismuth is metal. So thallium, lead, bismuth, polonium, astatine, and radium. So radon. These are all metals. Polonium is a radioactive metal. Polonium is what? Radioactive metal. Astatine is also radioactive metal. So astatine is not a metal, it's a halogen, but still it is non-metal. And thallium, lead, bismuth, polonium, all are metals. And boron, carbon, nitrogen, oxygen, fluorine, all are non-metals. So every p block element starts with a non-metal and ends with a metal. So metallic character on moving down the group increases, because from non-metal it changes to metal. So metallic character on moving down the group increases in any group, not only in this group, any other group also. But in this group, why we'll specially discuss, because first in all the p block elements starts with non-metals, that is boron, carbon, nitrogen, oxygen, and fluorine. These are all highly non-metallic in nature. And as we move from left to right, the non-metallic character decreases, non-metallic character increases, metallic character decreases. And as we go down the group, so here you can write here, as we move from, as we come across period, as we come across a period, please note down the statements. As we come across period, metallic character decreases, non-metallic character increases. Metallic character decreases from left to right, decreases from left to right, and non-metallic character, non-metallic character increases. Similarly, as we go down the group, as we go down the group, down the group, metallic character increases from top to bottom. Metallic character increases from top to bottom, from top to bottom, and non-metallic character, non-metallic character decreases. So in any group you'll find the same. In any period you'll find the same. So across a period, what happens? Across a period, metallic character decreases from left to right. Even you take first period, second period, third period, fourth period, fifth period, sixth period, seventh period. In all the periods across a period, metallic character decreases from left to right and non-metallic character increases. In a periods will come across left to right. Whereas In a group, down the group, you'll see down the group. Down the group, non-metallic character decreases and metallic character increases. So metallic character increases from top to bottom and non-metallic character decreases. So this is a general trend observed in all the periods and groups, which we have discussed already this in periodic classification of elements. So please note on these two statements so that you will not get any confusion. Next. So I'm giving time to write that statement for you. So please note on these statements. It's very, very important. Next continuation. Oxidation states. P block element shows both positive and negative oxidation states. As we move down the group, the lower oxidation state becomes less stable and other oxidation state becomes more stable due to inert pair effect. What is inert pair effect? Very, very important. So if you see P block elements show both positive and negative oxygen states. So for example, nitrogen will show from -3 to +5. So they shows positive as well as negative oxygen state. As we move down the curve, the lower oxygen state becomes less stable and the other oxygen state becomes more stable due to inert pair effect. For example, nitrogen -3 oxygen state is more stable, whereas bismuth of the same group +3 state is more stable. This is due to inert pair effect. What is inert pair effect? Very, very important. Please note down. This inert pair effect is observed in all the P block elements. Only in P block elements it is observed. P block elements only it is observed. This is inert pair effect is observed only in P block elements. What is this inert pair effect? The reluctance of S electrons. The reluctance of, here I am writing the definition. Please note it down. The reluctance of S electrons in bonding with other elements, with other atoms or other elements, with other elements is called as inert pair effect. Is called as inert pair effect. What is reluctance meaning? Reluctance means non-involvement. Reluctance means what? Non-involvement. For example, you can see bismuth. What is the configuration of bismuth? NH2 NP3. So bismuth is stable. It can form +5 also because of losing all the 5 electrons, +5 also. But bismuth is more stable in +3 because only p electrons are removed, s electrons will not be involved in bonding. So that's why since s electrons are not involved in the bonding, they are that is called as inert pair effect. And due to inert pair effect, for bismuth instead of having +5 oxygen state, +3 is more stable. +5 oxygen state, +3 is more stable because due to inert pair effect. This point is very, very important and it is observed only in P block elements. Inert pair effect is observed only in P block elements. Very, very important. Please note down. So now we are discussing entire P block, but in 11th class we'll discuss only group 13 and 14. So now we are going to start after finishing all these points, basic points for entire P block. Next, nature of bonding. Due to their size and availability of vacant d orbitals makes them capable of forming pi bonds. So the first members of p block elements, except for noble gases, they form p pi bonds to itself and to second row elements. So carbon carbon p pi double bond C triple bond C, N triple bond N, C double bond O, N double bond O, C triple bond N. So the first members of p block elements, except for noble gases, they form p pi bonds because p orbital of carbon combines with p orbital of another carbon to form pi bond. So that is why it is called p pi bonds. Similarly for nitrogen, carbon monoxide, nitrogen oxide, cyanide, etc. Heavier elements, that is the down group elements, that is bismuth, etc., do also pi bonding as d pi or d pi d pi. D pi or d pi bonds. Next continuation. So these are the trends in P block elements of entire, that is 13 to 18 group. Now we are going to discuss only 13 group and 14 group elements in this class lecture. As I told you, 11th class we'll discuss only 13 group. Now we are going to start only 13 group elements. Later we'll start with 14 group elements. So we'll continue with 14 group elements. So please listen carefully now. So those are the general trends so far we have discussed. Now we are going to discuss P block elements, 13 group. So, introduction. Just wait. So now we are discussing only 13th group, boron family. Yes, elements of 13th group. Now we are going to start. So please listen carefully, because in 11th class we'll study only about 13th and 14th, whereas in 12th class we'll study about 15, 16, 17, 18. However, in the entrance exam we'll write for both the years, so that's why it is mandatory to study all at a time. Next, group 13 elements. It is also called as boron family. So what does it consisting of? Boron, non-metal, aluminium, metal. Gallium is the only liquid metal as I told you. Indium and thallium also metals. Indium is metal and thallium is also metal. So these are the elements of group 13. That is boron, aluminium, gallium, indium and thallium. Boron is non-metal, aluminium is metal, gallium is liquid metal, indium and thallium also metals. These elements shows general electron configuration of Ns2 Np1. Only one electron in the p subshell. So boron, helium 2s2 2p1, gallium, argon 3d10. 3d10 is important here. 4s2 4p1, thallium 4f14 5d10 6s2 6p1, aluminium 3s2 3p1, neon gas configuration, and indium krypton 4d10 5s2 5p1. So these are the common outermost electron configurations of 13 group elements. So please note down in your classwork, all these electronic configurations are very, very important. Next continuation. Boron occurs in the earth crust in quantity less than 0.0001% by mass. It's very rare. So its important minerals are borax or tincal, Na2B407.10H2O, kernite, Na2B407.4H2O, orthoporic acid H3BO3, colomonite, Ca2B6011.5H2O. And boron exists in two isotopic forms, B10 and B11 respectively. So B10 and B11. So B11 is more, so we'll consider only B11. So this is the atomic mass of boron. What is the atomic number of boron? It is 4 or 5. 5. So 511. Next continuation. Aluminium, very, very important. Aluminium is the third most abundant element in the Earth's crust and first abundant most and the most abundant metal. If you take into metals, aluminum is the most abundant. Abundant means what? Availability. So aluminum is the most abundant metal in the Earth's crust, whereas aluminum is the third most abundant element in the Earth's crust. First most abundant element in the Earth's crust is oxygen, then nitrogen, then we have aluminum only. Oxygen is the first most abundant element. Next we have silicon. Next we have aluminum only, not nitrogen. We have silicon. Sorry, silicon in the form of sand. So its important minerals are corundum, Al2O3, diaspore, Al2O3.H2O, alum stone or alunite. This is also used for purification of water. So there is potassium sulfate, aluminum sulfate along with aluminum hydroxide. This is called alum. Alum is used for purification of water. Purification of water, we use alum. If you keep this alum stone in the tank, overhead tank of your house, it will purify the water. Purification of water. Sorry, purification of water. Next, feldspar, KALSITO. These ores farmers they'll ask in the examination. Bauxite, mainly aluminum is extracted from bauxite only. Bauxite is mainly aluminum is extracted from bauxite only. Is extracted from bauxite. Is extracted from bauxite only. Next, these are the important ores of aluminium. So that's why it is aluminum is the third most abundant element in the Earth's crust and most abundant metal in the Earth's crust. Metal. Within metals, it is the top metal, abundant metal in the Earth's crust. Top means abundant means more occurrence. It is availability. Next, gallium, indium, and thallium are less abundant elements in nature. So boron is less abundant. Gallium, indium, and thallium are less abundant. In this group, which is the most abundant element? Aluminium. Next continuation. atomic radii. Very, very important. Down the group, atomic radii increases from boron to thallium. Atomic radii increases from boron to thallium, except for aluminum to gallium. We observe 145 picometers to 135 picometers respectively. Why? Because gallium has because only gallium, the atomic rate is decreasing because gallium has, what is the configuration of gallium if you take into consideration gallium atomic number is 31. It is argon 3d10 4s2 4p1 due to completely filled 3d orbitals due to completely filled 3d orbitals completely filled 3d orbitals in gallium, its atomic radius is less than aluminium. Its atomic radius is less than aluminium. Very, very important point. So the atomic radius order is boron less than aluminium, aluminium greater than gallium, gallium less than indium, less than thallium. Or simply, if you want, you can write like this: boron less than gallium, gallium is less than aluminium, aluminium is less than indium, indium is less than thallium. So these are the general trends of atomic radius among 13 group elements. This trend, whichever is exceptional, they'll ask. Why gallium is having less atomic radii than aluminium? Because it has 3d10 configuration for gallium. So due to completely filled 3d orbitals, gallium has less atomic radii than aluminium due to the addition of due to completely filled 3d orbitals. So please note down this point: due to completely filled 3d orbitals in gallium. So gallium atomic number is 31. So please note down this. So this is the trend of atomic radius as well as ionic radii. Ionic radii also the same trend follows. Ionic radii as well as atomic radii. Ionic radii as well as atomic radii, the same trend follows. Please note it down. Next continuation. Ionization enthalpy. Very, very important. Even ionization enthalpy. The ionization enthalpy of group 13 elements is lower than that of corresponding group 2 elements. This already we know because in group 2 we have completely stable configuration. So the ionization energies do not follow trend from boron to thallium. These values are as follows. Let us see the values. So boron ionization energy, first ionization energy, second and third they have given because they have NS2 NP1. So all are having NS2 NP1 configuration. So we have three ionization energy. First ionization energy only P electron. Second ionization energy S electron. Third ionization energy S in the S only second electron. So first ionization energy of boron is 800. Aluminium is less. Gallium is still less than aluminium due to stable configuration, and indium 58 and still lesser than indium. Indium is still and thallium it is suddenly increasing. Thallium it is suddenly increasing. Why? Why it is happening for thallium? Just make a note because they do not form regular trends. So thallium is higher than that of indium because of poor shielding effect of F electrons. In thallium we have F electrons. So thallium ionization energy thallium plus is greater than indium due to poor shielding effect of F electrons. Please note down this result. Due to poor shielding effect of F electrons in thallium. In thallium, due to poor shielding effect of F electrons in thallium, what happens? The outer electrons will be under nuclear influence. As the outer electrons will be under nuclear influence, so automatically more ionization energy is required to remove the electrons. So that's why for thallium it is more. So the trend follows like this. First we have boron, first ionization energy, boron greater than thallium, second highest is thallium. Next we have aluminium, sorry, next we have indium, sorry, least is indium. Next we have aluminium, gallium next we have aluminium, next we have indium. Finally we have indium. So this is the ionization enthalpies. As these are not following regular trend, definitely they'll ask in the examination. So boron greater than thallium, greater than aluminium, greater than gallium, greater than aluminium, greater than indium. So gallium and aluminium are to some extent they are almost equal. Also, you can say greater than or equal to, whereas indium is still lesser. So why them thallium? As we go down the group, the ionization energy should decrease. But why it is happening in thallium? Due to poor shielding effect of F electrons. Thallium is having unusual higher ionization energy due to poor shielding effect of F electrons. So as F electrons are not shielded properly in thallium, due to which what happens, the outer electrons will come closer towards the nucleus. As the outer electrons are coming closer to the nucleus, there much energy is required to remove that outer electrons. So that's say ionization energy of thallium is greater than indium, gallium, and aluminium. So please note and make of that. This order is very, very important. Definitely they'll ask in the examination. So coming to second electron, removal of second electron, they have higher ionization energy in second electron because of stable electron, because NS2 is completely filled. So we have to remove from completely filled orbital. So that's why more energy is required. So when compared to this, so do 2427, 1816, 1979, 1820, 1971. So again, the same poor shielding effect of F electrons. So the order for the second ionization energy is first we have boron, second we have gallium. So boron, gallium, and so on. So boron, gallium, next thallium, next aluminium, so indium, last aluminium. So the second ionization energy follows the order. You can see boron greater than gallium, greater than what? We have after 1971, we have thallium greater than decreasing order I'm writing, second ionization energy, greater than aluminium, no, indium, and finally we have aluminium. So this is the second ionization enthalpy order. So please make a note in your classwork. First ionization enthalpy order, decreasing order, second ionization enthalpy order, third ionization enthalpy order also we write here. First we have boron greater than 27442962, gallium again same. Next we have 2877, that is thallium greater than indium, and finally we have aluminium. Sorry, aluminium and indium. Aluminium and indium. So least is indium. So these are the trends of first ionization enthalpy, second ionization enthalpy, and third ionization enthalpy for group 13 elements. Please make it note why the first ionization enthalpy is more for thallium than any other elements except boron, due to poor shielding effect of F electron. This reasoning is also important. This order is also important. Generally, they'll ask first only. If they ask for second, third, also you can write. And second ionization enthalpies are more when compared to first. Why? Exceptionally more, because the second electron has to be removed from stable configuration, that is NS2. As the second electron is to be removed from stable configuration, that is NS2. So automatically the second ionization enthalpy is more when compared to first ionization enthalpy, far more. Next, please make a note of this. Next continuation. So generally we expected a regular decrease in ionization energies, but the decrease from aluminum to gallium to decrease in size and increase from indium to thallium is due to low screening effect of D and F electrons, as I told you. Why there is increasing from indium to thallium? Due to low screening effect or shielding effect of D and F electrons. That's why there is regular decrease in ionization energy. We will not expect. But from aluminum to gallium, the decrease in size and increase from indium to thallium is due to low screening effect of D and F electrons. This already I explained you. Next continuation, electronegativity. Down the group, the electronegativity first decreases from boron to aluminum and then decreases marginally from aluminum to thallium. Very, very important. Why it is increasing? That also we discuss. So electronegativity decreases from boron to aluminum effectively, but from aluminum to thallium, it increases marginally. Aluminum to thallium, it increases marginally. Even though actually the metallic character should increase, but still the electronegativity character is increasing because of discrepancy in atomic size of these elements. So due to the why it is increasing, due to The increase in effective nuclear charge due to the increase in effective nuclear charge because of poor shielding effect, effective nuclear charge due to the increase in effective nuclear charge and due to the presence of fully filled lesser shielding D and F orbitals and due to the presence of due to the presence of lesser shielding lesser shielding completely filled D and F orbitals completely filled D and F orbitals completely filled D and F orbitals. This reason is very, very important. Please make a note. Very, very important reason. So due to the effective nuclear charge increases, due to the increase in effective nuclear charge, and due to the presence of lesser shielding completely filled D and F orbitals, D and F electrons are orbitals present in between the valence shell electrons and noble gas core. The force of attraction of the nucleus for the valence shell increases, and the electronegativity also increases from aluminum to gallium. Sorry, thallium. So why the electronegativity character increases for gallium, indium, and thallium? In gallium, we have 3d10 configuration, and this we have 4f14 configuration, and this we have 5f14 configuration. So due to this, what happens? As due to the presence of completely filled, lesser shielding effect, completely filled D and F orbitals, the nuclear charge increases. Due to the increase in effective nuclear charge, what happens? The atomic size also increases. As the atomic size increases, the electronegativity character also increases. The electronegativity character also increases from gallium to thallium. So the electron negativity character, so the order of electron negativity decreasing order is boron greater than thallium. Thallium is equal to indium greater than aluminium. So greater than gallium and aluminium. Greater than gallium greater than aluminium. So this is the trend of electronegativity for 13 group elements. Why the sudden increase takes place for thallium, indium, and gallium? Why it is for these three elements? Due to the presence of lesser shielding completely filled D and F orbitals, due to which what happens? The increase in effective nuclear charge takes place. As the effective nuclear charge increases, electronegativity character also increases. Because of the force of attraction of the nucleus for the valence shell electron increases, so electronegativity character increases from aluminium to thallium. So please make a note. This reason is very, very important. Very, very important this reason. Please make a note. Next. So these are the trends of electronegativity among 13 group elements. Now, all these elements except boron are metals except boron, as I told you. All the elements are metals except boron. Boron is non-metallic in nature. So allotropes of boron is crystalline boron, amorphous boron. Crystalline boron is black and very hard. Amorphous boron is brown and chemically active. So the metallic nature increases from aluminium to thallium. Metallic nature increases from aluminium to thallium. Because down the group, the metallic character increases. So boron has extremely high melting point, even though it is non-metal, but still it has extremely high melting point due to its strong crystalline lattice. The other metals have low melting points. Gallium is the element with the least melting point, 303 kelvins, because it is liquid at room temperature. Gallium is what? Liquid at room temperature. So that's why automatically its melting point decreases. It is low. So what is the room temperature? 298 Kelvin. So it is liquid at room temperature. So gallium is the element with the least melting point. All these elements have high boiling points led by boron and decreased down the group. Gallium is having low melting point and high boiling point. It is used in high temperature thermometry. That's why it is used for high temperature thermometry due to its low melting point and high boiling point. And all the elements have high boiling points down the group, decreases down the group. The melting point, boiling points decreases down the group. So these are the general trends of melting points and boiling points. So general trends of melting points and boiling points. These are the general trends of melting points and boiling points. Next, the value of melting and boiling points are given below. Melting point of boron is 2453 kelvins, aluminum 933, gallium is exceptionally low because it is liquid at room temperature. Next 430 and 576. So the order of melting points in points. So there's the as these are not following a regular trend, all the orders of 13 group elements are very important. So decreasing order of melting points and boiling points if I write here. So melting points first will be decreasing order, melting points order. Boron first we have because it is 2453. Next we have aluminum greater than aluminum. Next we have thallium. Next we have indium and lowest we have gallium. Next, similarly for boiling point order, if you take boiling point order, if you take decreasing order, boron greater than aluminum, greater than gallium, greater than indium, greater than thallium. Regular trend it is following. Boiling point it is following regular trend. Since the melting point of gallium and boiling point is having lot of difference, that's why it is used in thermometric liquid. Gallium is used as thermometric liquid. Why? Because it can read a wide range of temperatures. It can read a wide range of temperatures that is from 303 kelvins to 2676. That's why it is used as gallium is used as thermometric liquid. This point is also important. Next, we have density. Group 13 elements have higher densities as compared to group 2 elements, and density increases from boron to thallium. Boron and aluminum have comparatively low values. So density increases from boron to thallium, and density of group 13 is greater than density of group 13 elements greater than group 2 elements. Group 2 elements because group comparison is important. So group 13 elements have higher densities as compared to group 2 elements because due to smaller size and ionic radii of group 13 elements as compared to group 2 elements, which makes density to increase. Down the group, the density increases from boron to thallium. This is due to corresponding increase in atomic mass of the element. Why the density is increasing? Because atomic mass of the element which outweighs the effect of increased atomic size. So the densities of boron and aluminum, however, quite lower than those of other members. So only boron and aluminum have comparatively low values. So please make a note of all these points. Next continuation. Chemical properties, oxidation states. So these are the physical properties we have done. All the physical properties are important. Now we are going to discuss chemical properties. Boron, with its very high value of sum of first three ionization energies, cannot show plus 3 oxygen state. It will show only minus 3. And for gallium and indium, plus 3 oxygen state is more stable than plus 1, which is due to inert pair effect. Gallium and indium, plus 3 oxygen state is more stable than plus 1. The relative stability of plus 1 oxygen state increases as we go down the group, as we move down the group. So thallium plus 1 state is more stable than plus 3 state. Very, very important point. Why? Because due to inert pair effect. In thallium, the s electrons will not involve in bonding. So as s electrons are not involved in the bonding, so thallium plus 1 is more stable than thallium plus 3. So definitely this is very important. Whereas for gallium and indium, plus 3 state is more stable than plus 1 state. So the plus 1 state increases down the group. Aluminum less than plus 3. Aluminum plus 1 is less than gallium plus 1 less than indium thallium plus 1. So trivalent species form electron deficient molecules. Very, very important. What are these electron deficient molecules? For example, if you see BCl3. So BCl3, if you take this is trivalent species. Trivalent species. So here boron has 3 electrons in its valence shell. So it combines with 3 electrons with chlorine. So I'll make it clearly for you. So boron configuration is BCl3. So it combines with 3 chlorines and forms BCl3. So after sharing, boron alone has only 6 electrons in the valence shell. 6 electrons after sharing. But after sharing, an element should have 8 electrons. Element should have 8 electrons. But that's why these are called as electron deficient species. electron deficient species. So these electron deficient species are also called as Lewis acids. Electron deficient species, and they are also called as Lewis acids. They are also called as what? Lewis acids. Here do not have place, that's why I'm writing here. Please try to understand. So all the electron deficient molecules are Lewis acids. Why they are called as Lewis acids? Because they are ready to accept electron pairs. They are ready to accept electron pairs. Since after sharing, boron has only 6 electrons after sharing. That's why it is called electron deficient species. So all the trivalent species form electron deficient molecules. All the trivalent species forms electron deficient molecules. Please make a note of this, children. Very, very important. So the trivalent species of 13 group elements are Lewis acids. Why? Because they are all electron deficient molecules, as I told you. As these elements form electron deficient molecule, they act as Lewis acids. The Lewis acid character decreases with the increasing size of the element. BCl3 acts as good Lewis acid when compared to AlCl3 because BCl3 adds to ammonia more easily than AlCl3. And BCl3 combines the ammonia and forms additional product by the means of coordinate covalent bond because ammonia is donor and BCl3 is acceptor, coordinate covalent bond. This is a special type of bond. So BCl3 is acceptor because it is accepting and ammonia is donor. BCl3 is acceptor, ammonia is donor. So coordinate covalent bond. So please make a note of this, children. Very, very important. Next continuation. AlCl3 and other metal halides, aluminum chloride and other metal halides of this group form dimers. Dimers means two molecules, halogen bridging, that is Al2L6. So AlCl3, that's why aluminum is having diagonal relationship with beryllium because beryllium also forms dimers, which you have seen in the previous chapter. So aluminum beryllium forms dimers. Dimers means two molecules combined together. So AlCl3 should be there, but Al2Cl6 is present. AlCl3 does not present. AlCl3 is not stable. Is not stable, but it's a Lewis acid, and Al2L6 is stable. Al2L6 is Al2Cl6 is stable. Thus, the monoic trihalides of these elements acts as strong Lewis acids. Monoic trihalides acts as strong Lewis acids because they can readily accept electron pair because they can readily accept electron pairs. They can readily accept electron pairs. That is very, very important. Please make a note. So aluminum exists as dimers. Aluminum chloride exists as dimer. Very, very important point. Next, hydrolysis of third A group elements. In their trivalent state, these compounds being covalent hydrolyze in water. They can readily hydrolyze in water. Trihalide form from species like MOH4 minus MOH6 plus 3 upon hydrolysis. They form trihalides, that is BCl3 on dissolving in water forms BOH taken 4 times minus and AlCl3 on hydrolysis forms AlOH taken 6. Apart from beryllium, boron, aluminium, indium, gallium will form 6 because their covalence is 6. Their covalence is 6, and for boron, its covalence is only 4. Aluminum chloride forms octahedral AlH2 taken 6 times plus 3. And in this, aluminum undergoes sp3d2 hybridization. What is hybridization? sp3d2. All boron trihalides except BF3 are hydrolyzed to boric acid. They form boric acid, that is H3BO3. Next continuation. So this is the hydrolysis of 13 group elements. Now let us see some questions based on this. The p-pi back bonding occurs in halides of boron and not in those of aluminum. Explain. Since aluminum has large size than boron, the back bonding is not possible. So in boron, we have p-pi back bonding occurs in the halides of boron, BCl3, BF3, etc. BCl3, BF3, etc. P by P by back bonding takes place because aluminum has large size than boron, so the back bonding is not possible. What is this back bonding? I'll just write here. Please note, make a note. Back bonding in BCl3. Back bonding in BCl3 or BF3. Let us see. Back bonding. I'm writing here. Please note down. In BF3, let us say all trihydrides are boron. So boron has empty p orbital. Boron has empty p orbital. Why? Because it is np1 only. Np p orbital of fluorine and p orbital of fluorine and p orbital of fluorine. P orbital of fluorine contains lone pair. Contains what? It contains lone pair, and hence boron acts as Lewis acid and fluorine acts as Lewis base. Fluorine donates its lone pair to boron and donates it and donates donates it, and this bonding is called as back bonding and donates it, which results in the back bonding. So what is here back bonding? Boron has empty p orbital and p orbital of fluorine contains lone pair of electrons, lone pair of electrons. So and donates it to boron by the means of this bonding is called as back bonding. This bonding is called what? Back bonding. Since aluminum has large size than boron, the back bonding is not possible. Whereas for boron it is possible because of fluorine content. So here boron acts as Lewis acid. In BF3 boron acts as Lewis acid and fluorine is donating its lone pair, so that's why it is acting as Lewis base. Lewis base. So this is called back bonding. So boron has empty p orbital. Empty p orbital, why? Because in boron only one p orbital. One p orbital means it can extend up to maximum. Still, this is empty. This is also empty. So since boron has empty p orbital, fluorine contains lone pair of electrons in p orbital. So in p orbital and donates it to be a boron atom. So which is called as back bonding. So please make a note what is back bonding. So the p-pi back bonding occurs in halides of boron, not in those of aluminum because aluminum has larger size than compared to boron. So just I want to discuss what is back bonding. I have discussed it. Please make a note. Next continuation. Boron and aluminum halides behaves as Lewis acids because they are electron deficient species. Electron deficient species. As they are electron deficient species, they are acting as Lewis acid because after sharing BF3, so you can see here boron trifluoride. So each fluorine will share one electron. After sharing, boron is getting only 6 electrons. After sharing 6 electrons after sharing. But according to octet rule, they should contain after sharing 8 electrons. That's why they are called as electron deficient species. Electron deficient species, very, very important. Please make a note. As electron deficient species are ready to accept electrons, so they are called as Lewis acids. What are Lewis acids? The substance which can accept electrons readily, they are called as Lewis acids. So to complete octet, they can accept a lone pair of electrons from a donor and thus act as Lewis acid. Simple words. So this is clear. Next question. So to complete octet, they can accept a lone pair of electrons from a donor and thus acts as Lewis acids. Next question. Aluminum forms AlF6 minus ion, but boron does not form Bf6 minus, and because due to non-availability of the maximum coordination number of boron is 4 as it does not contain d orbitals. The maximum covalency of boron is 4 only. That is coordination number, covalency, both are same. Covalency and coordination number both are same is only 4. as it does not have d orbitals, while the maximum coordination number of aluminum is 6 because it contains d orbitals. It contains d orbitals, empty d orbitals. Aluminum can expand its octet because it contains empty d orbitals. Next continuation. So these are the questions just we have discussed right now, and more questions we'll discuss in the next coming topic. So these are the chemical properties. We have done only oxygen states and hydrates and halides only. More about chemical properties we'll discuss in the next session. So with this, I'm ending this session. So please follow what we discussed so far. All these points are very, very important. Please make a note of it. And with this, I'm ending this session. Thank you all.